Alrighty, welcome back. We're working here with experimental probability and theoretical probability, where they come together. Our prerequisite skills we are relying on here, we're relying on your ability to calculate an experimental probability and your ability to calculate a theoretical probability when we're rolling two dice. Now, directly from our lesson on theoretical probability here, I have all of our data that we put together summing up the values of two different dice. I'll encourage you right here to pause the video. I want you to calculate the theoretical probability of rolling a 7 when we roll two dice. Pause the video here, come back to see how we do. Good, so we're taking the possible successful outcomes against our total possible outcomes. When we're working right here, we have 36 different possibilities, 36 different ways of rolling two dice. That's our total possible outcomes. And our possible successful outcomes, because we're looking at rolling a 7, we can see 1, 2, 3, 4, 5, 6 different ways to roll a 7. So our numerator here is 6. Now we can reduce this fraction right here. 6 over 36 is another way of writing 1 over 6. If you would like to turn that into a percentage, that's 1 divided by 6 times 100. We're working with 16.7%. Fantastic. Now, that means we're expecting 1 out of 6 times to roll a 7. That means 16.7% of the times we roll a pair of dice, we're expecting a sum of 7. Fantastic. So we have already relied on our ability to calculate a theoretical probability of two dice. Now, even further, so then let's just say we have this experiment going on. So we're rolling two dice, we're counting, we're tracking how many 7s are rolled. And really, my question for you here is, are these dice trustworthy? Well, if we roll dice one time, okay, and what do we roll? We roll something that's not a 7. So the number of 7s rolled is a 0. I'll encourage you right here, pause the video. I want you to calculate the experimental probability now of rolling a 7 in just this situation where we have only rolled dice once. Go for it. Good, so we're taking the number of successes over the total trials, nice and easy. That is 0 successes over one trial. That is 0% of the time we have experimentally rolled a 7 right here. Our experimental probability is 0%. Okay, well that's only one roll. I don't know if that's quite enough to say, hey, I don't trust these dice. So let's just check another situation right here. Let's say we have continued to roll the dice 9 more times. Of those 9 times, we've rolled a 7 only once. Well, I want you again to adjust the calculation you've performed and determine what is the experimental probability here now of rolling a 7, now that we've rolled 10 times, one of them a 7. Good, okay, so right here, that is a 10% chance of rolling a 7. Now, we have still only rolled the dice 10 times. If you're playing a board game, there are 2 dice, you're rolling them 10 times. Would you believe it if you got a 7 only one of those times? Absolutely. I mean, honestly, 10% is not really that far from the 16.7% that we're expecting because, in this case, because we have only rolled these dice 10 times. Again, I want you to perform this same activity. This time, we have rolled 5 7s. By the time we've rolled 15 times, we've rolled 5 7s. I want you to make an adjustment to your calculation and determine what is our new experimental probability. Okay, so at this point, we rolled a 7 1/3 of the time. That is 33% of the time, which is almost twice as much as our experimental probability, as much as our theoretical probability. But that being said, we've only rolled these dice 15 times. If you play a game and you've rolled a 7 5 times by now, you say, wow, it's been rolled a lot, but is that enough to say, wow, these dice are untrustworthy? No, I certainly don't think so. That is certainly within the realm of possibility, and it is certainly within the realm of expectation to roll 7 5 times out of 15 sometimes, right? We still have not quite performed enough calculations. Next, okay, so we've continued to roll these dice not 1 time, not 10 times, not 15 times. We have rolled these dice 100 times. We've only seen a 7 pop up 6 times. Now I want you to perform one more calculation right here. Calculate the experimental probability of rolling a 7. Good, okay, so right here we have an experimental probability of 6% of the time. pretty low, very low actually, when we compare it to our 16.7% expectation. We have now rolled these dice 100 times. That's a lot. That's might not be enough to say, hey, there's something wrong with these dice, but right? I encourage you one more time under this same experiment. Let's say they continued to roll not 100 times, but they did that in itself 10 times. They rolled the pair of dice 1,000 times. They found 61 sevens. And I want you to calculate the new experimental probability of rolling a 7. Good, so we should end up here with 6.1% of the time. Now at this point, we have rolled these dice 1,000 times. If we've rolled these dice 1,000 times, and our experimental probability, that is what we have observed, is way less. That is less than a third, that's almost a third as much as our expected, as our theoretical probability that we calculated earlier, I would say these dice are not trustworthy. I would not like to use these dice to play a game unless that game is avoiding a 7, because these dice certainly do not roll a 7 as much as expected. Let's look at scenario 2. Okay, so these are a new set of dice. Now these new set of dice, again, I want you to calculate the experimental probability with 1 7, 1 roll, then the experimental probability of 3 7s and 10 rolls, 3 7s, 15 rolls, 18 and 100, 176, and 1,000. I want you to perform 5 different calculations. This will tell a story of what's happening right here. I want you to pause the video here, come back when you've performed your calculations. So what's happened here is we've rolled these dice one time, and we got a 7. That was 100% of the time. Still not enough to say anything in particular. But then we go and we roll the dice 10 times, and we end up with a 30% experimental probability. Okay. Again, kind of some wonky numbers because the number of dice rolls is still not very high right here. Now it's down to 20%. Then we've rolled 100 times. That's 18%. Okay, now that seems a little bit more reasonable. And finally, down to 17.6% of the time once we have completed 1,000 rolls. My question is, are these dice reasonable? Well, let's remember, we're comparing this to a 16.7% number. That is the theoretical probability we're expecting. We end up with 17.6. That seems pretty darn close to me. I certainly would trust these dice. I'd like to play a game with them. The conclusion here, the idea is that if you are rolling dice, if you are doing anything that you can calculate a theoretical probability for, if you perform enough, if you perform a sufficient number of trials, that sufficient number is not 1. That sufficient number is not 10 nor 15. It might be 100. It likely is 1,000. We're looking for a huge number of trials. If we perform a huge number of trials, we're expecting our experimental probability to tend toward. It will go toward, although it will not end up, it may not end up at that number unless you continue to perform the trials, but we expect these numbers. Let's take a look. We see that they're getting closer and closer and closer to our 16% number, to our 16.7% number. This is what we would expect if we have trustworthy dice. That is, the experimental probability tends towards theoretical probability with sufficient number of trials. If you followed along, I'm hoping you know what to expect after performing an experiment a sufficient number of times.
Here.